Okay, we're going to be having a look at representing vectors. Now, you've probably been quite familiar with representing vectors from some bits in GCSE. Can you think about which topic you might have looked at representing vectors with, or using vectors, maybe I should say, in GCSE? Which topics has it come across in GCSE? Yeah, in transformations. Can you be more specific rather than transformations? Translations, yeah. And actually, we knew in translations what the top part and the bottom part corresponded to. What does the top value in a vector correspond to, Mabel? The across direction, yeah. And I suppose if we make that sound more A-level, rather than saying the across direction, what could we say? Yeah, the x direction. And actually, when you think of the x-axis, it kind of makes sense because we know positive numbers go to the right and negative numbers go to the left. So if it's a positive number at the top, it's obviously corresponding at a positive direction, okay? And then obviously that must mean that the number at the bottom is going to be the y direction. We know that with a translation, the bottom number meant how much the shape moved up or down. I can actually give you a bit of a preview of what will change when it goes to year 13. Any ideas of what you think might change in year 13 if we've got one thing representing left and right, one thing representing up and down? What else could happen if we wanted to do something extra with them? Pardon? Yeah, we could do a third dimension. So when we go to year 13, we recap this topic and we add in the third dimension, which wouldn't be the x-axis, the y-axis, it would be the z-axis, which makes things become 3D. And that's where vectors really, really become interesting because you then get to model things moving in three-dimensional space. Yeah, so the z-axis is perpendicular to the y-axis and to the x-axis. Okay, so I've written here, you should already be familiar with that the value of the vector is the displacement in the x and y direction if it's in 2D. We just said how it would move into 3D, you could have the x, y, and z. So here, I've drawn the vector A, which is 3 minus 2, and it's moving 3 across in this direction, in the x direction, and then 2 down. But also you could notice that you could see it as moving 2 down and then moving 3 across. Either way, it's describing the same displacement, okay? I then also added in this vector B, which is 0, minus 1. What would 0, minus 1 look like as a displacement? It's just going down one space. So I'm actually going to add this B vector here. I'm going to add it to the end of this vector. And I'm just going to say that this one is 0, minus 1. And we're going to think about, first of all, adding these two vectors together, which is 3 minus 2 and 0 minus 1, which again, you will have seen this from GCSE. When you add these two vectors together, what would we say is the way of adding vectors together? Add the top, add the bottom. You can just do that with vectors. So when you add the top, we've got 3 add 0, which is 3, minus 2 add minus 1, which is minus 3. So we just come up with this vector, which is just 3 minus 3. What, though, is the geometric significance of this? And when I say the geometric significance, I mean kind of thinking about the diagram that we've drawn. How does this 3 minus 3 relate to what we've just drawn here? Have a think and just tell the person next to you if you think how this 3 minus 3 connects back to this diagram. I'm just going to give you 30 seconds to think about that. Okay, so Hassan, what did you and Ishak talk about? Where do you think this 3 minus 3 is represented on the diagram? Sorry? Good, how far the original point moves. The original point is going to go 3 across, and it's going to go 3 down, and it actually winds up here. This should remind us of something that we said in the first lesson on vectors. Does anybody remember what the law of this is called? You can have a look on your first page if you need to. Pardon? Yeah, the triangle. Yeah, the triangle law of vector addition. We can see that that pathway we said was the same as that pathway plus that pathway put together. So it's just kind of nice to see that it also works out in terms of the geometric significance as well. Okay, so 2a is just 2 multiplied by the A vector. We've got that scalar 2 outside the front, which just means you're going to make something bigger. Very obviously, we're just going to multiply the top and bottom part, the x part and the y part, by 2. So we get 6 and minus 4. Now, if I was going to draw 6 minus 4 onto my grid, what would you expect to see? And try and give me as much information as possible if something was drawn as 6 minus 4. Yeah, the length of the line would be twice as long. And can you tell me anything else about that, Araful? If the length of the line was twice long, I still think there's more information you can give me. It's 6 across and 4 down. Is there any other comparisons? I mean, maybe I can draw it on and it might sort of help out a bit. Let's see if I can fit this in. 1, 2, 3, 4, 5, 6 across. 1, 2, 3, 4 down. Good. They're going to be parallel. Which one is going to be parallel? To which vector? Yeah, this is 2a here. This one at the top here was a. And we can see that those two line segments that we've drawn, not only is the purple one double the length of the other one, but it remains parallel. Do you remember we looked at that on your front page with those GCSE summary? If you multiply a vector by a scalar, it stays in the same direction. There's only one time it sort of stays in the same direction, but it reverses. When would a vector reverse its direction? Pardon, Araful? When it's been multiplied by a negative number. It would be in parallel, but it would have just flipped its direction. Okay, so that's still sort of a GCSE recap there, but I kind of like seeing some of these things that we've got. Now, I've also written, which has maybe got a little bit confused with this purple line that I've drawn here, we've also got this important fact here. This is some new notation that some of you may have come across before, maybe some of you haven't. It says a unit vector is a vector of magnitude 1. Very quickly, remind me what magnitude means with vector. Size, length, okay? So a unit vector, that word unit means that it has a length of 1. We use the letters I and J, and when you write I and J, you will underline I and J, because that's how we denote that something is a vector. On a computer, it is typed bold, but we obviously can't write bold, so we underline it. The unit vectors I and J are unit vectors in the x-axis and y-axis direction respectively. So I is 1, 0, and J is 0, 1. A couple of ways you can remember that it goes in that order. The alphabet goes X, Y, Z. The alphabet goes I, J, K is going to be the one you come across in year 13, okay? Another thing that I think someone told me is J goes up because J is like jump. I know, just silly things of ways you might quickly memorize these things, because that's sometimes where people make a mistake. So you can see here, 4, 3 is the same as 4 lots of I plus 3 lots of J, which gives you 4I plus 3J. Okay? Is this microphone like coming out of the board? Does it sound like my voice is louder? No, I think I'm just paranoid then. Because in the other classroom I did it and it made it sound like louder. It was very odd. Okay, so we're very quickly going to translate these things from in their I and J form and put them into vector form. It's not going to be very tricky at all. So if I wanted to write A in column form, what would it look like if it was put in column form? 3 and then a 0 to show that there's nothing down here. So we've already answered part 1 of this to write A in vector form. It then wants us to find B plus 2C in IJ form. This is probably going to sound a bit silly, but I actually think it's better to put everything into column form to do your calculations, and then if you need to, you put it back in I and J afterwards. You'll find putting it in column form just makes things a little bit easier. So in column form here, what would B be in column form? And C? 1 minus 2. So if we want to work out what B plus 2C is, it will just be B plus 2 lots of C, and then we just do it as we'd expect to here. So we get 1 plus 2 times 1, which is 3. In fact, I'd probably like to do this line. 1, 1 plus 2 minus 4. So you get 3 for the I components and 1 minus 4, which is minus 3. Okay? Make sure you've got all those bits written down. We're going to have a look at the next page. Oh, in I and J form, correct. So we should write that back as 3I minus 3J. Okay, I'll just give you 30 seconds to finish writing that bit down, and then we'll have a look at the next page together where you can do some practice for me. Okay, so I'm going to just do these two questions at the top, and then you're going to do this bit up here, and you're also going to have a look at this question for me in just a second as well, okay? So let's read through what's going to happen up here. We're going to be using some things to do with our column vectors, and we've got some new symbols here that I want to talk to you about. It says, given that C equals 3i plus 4j, and D equals I minus 2j, find this weird symbol. It's going to tell you what this weird symbol here is. It's like an upside down Y. You draw it by doing that line first, and then by adding this line in afterwards. Okay, it's called lambda, and it's just a scalar. Any idea where lambda might have come from? It's a Greek letter. Yeah, it's a Greek letter. So the way we draw that, I'll just draw it a couple more times. It looks like an upside down Y. You draw like that bit first, and then that bit. So it's that bit, and then that bit. All it is just a new letter that we use. We kind of ran out of letters in maths, so we stopped using the Latin alphabet, and we start using the Greek alphabet as well. So we're going to try and find out what lambda is, and it says if C plus lambda D is parallel to I plus j. So there's quite a few things that are going on here. Looks like we've got this thing here, first of all, that we're going to work out. Then we've got something that it is parallel, and then we've got another vector. We'll deal with this thing first, and then we're going to come back to what the word parallel will mean with vectors. So we're first of all going to say what C plus lambda D is actually equal to. So C is 3, 4, plus lambda, and D is, what's D going to be in vector form? 1 minus 2. So that becomes lambda minus 2 lambda, multiplying by lambda there. I'll give you a bit more time to write this up because you're probably getting used to writing lambda for the first time. So all we did, we wrote C plus lambda D, we multiplied these by lambda, and then we're going to add them together and write them as a single vector. So we should have 3 plus lambda, 4 minus 2 lambda. That is what C plus lambda D is. So we've dealt with that first thing that I've put the box around. We now want to start thinking about the second half of the question, where it says it's parallel to I plus j. If you finish writing it down, just think, how do we know if two things are going to be parallel as vectors? And that first page could be helpful. What was that, Kausa? Yeah, good. Parallel means that they are multiples of each other. So parallel means is a multiple of. So this must mean this is a multiple of this. Good. So let's just say, I'm going to do it in a way that might seem a bit long, but it's going to help you to do the future questions, okay? So we're going to say that 3 plus lambda, 4 minus 2 lambda is a multiple of 1, 1. Sometimes we could use any letter here. Let's just use one we're kind of familiar. Yeah, we could use K, we could use C, we could use X, but it's just a multiple of 1, 1. You don't necessarily need to do this in quite this complex one for something that's so simple as 1, 1, but trust me, it will make your life easier for some of the tricky ones that come up. So we've come up with, when we multiply the 1, 1 by x, we come up with x, x. Now what do you think we could do at this stage that we've got here? They're equal to each other, so what bits do you want to make equal to each other, Ishraq? Yeah, we've actually got like the I component, which is the top part, we get 3 plus lambda equals x. That's coming from the I component. The j component, which is the bottom part, is 4 minus 2 lambda, must also be equal to the same thing. They're not equal to 1, they're equal to... So now we can solve it to find lambda. Ishraq went straight in and just said, okay, well that bit is going to be equal to that bit, because he could just tell that these things were here. So in this very simple one, we know that the top part must be equal to the bottom part in order for it to be a multiple of 1, 1. But they do get trickier when you have different values that you might have in here, which is why I usually prefer to do this method of multiplying by a constant. So if we say that these two things are now equal to each other, we get 3 plus lambda equals 4 minus 2 lambda, and we just solve that equation by adding your 2 lambda to this side. So we get 3 plus 3 lambda equals 4. 3 lambda equals 1. So lambda is equal to a third. How could we check to see if our answer seems sensible? What could we do with the value of lambda? We could substitute it into the expression for c plus lambda d. So we would get 3 plus a third, and then 4 minus 2/3. And then you've got that the top and bottom are the same as each other, which means that it's parallel to ij. So I'm just going to do c, and then you're going to do part b and part d, okay? So we're now going to have a look at doing C. You may not have enough space to do this one on your page, but I wouldn't worry about it. You might just want to listen to this one. So we've now got C minus SD. They're using the variable S. When you use the variable S, careful, it doesn't look like a 5. So we have C minus SD. Well, C is 3, 4, and we're minusing S lots of 1 minus 2. I'm going to go a little bit quicker here. 3 minus S times 1 is just 3 minus S. 4 minus s times minus 2. What do we do with the minus s and the minus 2? Plus 2s. So it's going to become 4 plus 2s. So we want this thing, which is 3 minus s, 4 plus 2s. I want it to be parallel. What do I want it to be parallel to this time, Shahan? 2 and 1. And I'm going to still use my x to show that this is a multiple of this vector. Then I can see, let's see if we can go a little bit quicker here. Actually, let's still do that extra one. We get 3 minus s, 4 plus 2s is equal to 2x, x. What did we then extract from that next? Yep, so the I parts we said were equal. 3 minus s is 2x, and we also get that 4 plus 2s is equal to x. What do we then do with these equations? Sub that one into that one, so you end up with 3 minus s equals 2 lots of 4 plus 2s, and then you solve the equation. 3 minus s equals 8 plus 4s. Add the s to this side, and subtract the 8. And you get minus 5 equals 5s. So, why? Yeah, I know you've got to draw your s's smaller than your 5s to make them look different. They love using the letter s in vectors, and it's so annoying. And then that must mean that s is equal to minus 1, okay? So you've seen me do one a bit slowly, one a bit quicker. You've got 2 of them that I want you to try down here. And then you've got one of them down here that has the word resultant. Resultant means the vector which is the result of 2 or more other vectors added. We talked about that earlier. It's the triangle law of addition. So the resultant one, it's actually asking you to think about A and B added together. Okay, so you've got to try, you won't have enough space here, you might need to do this in your books instead. You need to do question B, question D, and then this one you've got down here. Probably about 10 minutes to try these ones here, okay?